Hello everyone, welcome to my new lecture series. Myself Vignesh, working as an assistant professor in Department of Mechanical and Mechatronics Engineering in SNS College of Engineering. And in this lecture series, we are talking about the basic thermodynamics problem based on the first law of thermodynamics. And in my previous videos, we have seen about the closed system problems, and in these videos we are going to talk about the problems related to the open system where steady flow energy equation will be there. Okay, so the next problem will be write it down. In a thermal power plant operating in a steady state, an adiabatic steam turbine receives 1 kg per second of superheated steam at 3 megapascal and 400 degrees centigrade. Okay, the steam enters the turbine with a velocity of 10 meter per second at an elevation of 10 meter above the ground level. Okay, and the steam leaves the turbine at 0.1 bar with 10% moisture content. The velocity of the steam at the exit is 30 meter per second, and the exit is at the elevation of 4 meter above the ground level. Here they are talking about the potential energy, so that elevation has been given, it is not placed in the ground. So the turbine has been elevated at certain portion, certain meter above the ground level. So we are going to talk about in this problem the potential energy is also be considered, and the change in enthalpy is minus 887 kilojoule per kg, and we need to calculate the power output of the turbine. Okay, so write down the steady flow energy equation first. This is the turbine where superheated steam enters the turbine. There will be some work transfer will be there, and the properties will be changed at the outlet of a turbine. So all those terms has been given, right? And the potential energy, that is the turbine is not at the ground level, it is elevated to certain portion. So those terms that 10 meter above the ground level and 4 meter above the ground level will play a major role. Okay, so in my previous problems that potential energy has been neglected, because that turbine or nozzle or whatever may be the device that has been placed in the ground level, so that we can neglect the potential energy, but here we are going to consider the potential energy as well. Okay, so write down the given properties, that is T1 will be has been given, and velocity has also been given, and potential energy, that is ground level, has been given, and mass flow rate has been given. Okay, pressure has been given, pressure at the outlet has been given. So write down all these terms. Okay, what we need to find out is power output. Okay, so first we need to write down the steady flow energy equation first. So Q minus W is equal to M into H2 minus H1 plus C2 square by 2 minus C1 square by 2 plus Z into Z2 minus Z1, where Z is the constant value as 9.81, substitute that term. Okay, so the enthalpy, change in enthalpy is also be given. Write it down, that is minus 887. Here there is no heat transfer between system and the surroundings, so Q will be 0, only the W, work done, will be taken care of. That we need to find out. Okay, so substitute all the terms, you will get work done as 886.54 kilowatt. Okay, so this much of power output has been generated in the turbine, and what percentage error will be introduced by ignoring changes in kinetic and potential terms? So you can ask, right, in your previous videos you have neglected that kinetic energy and potential energy, and if you here also, if you neglect those terms, okay, kinetic and potential energy, and what happens to that work done? Okay, will it be same, or is there any percentage error will be there? So we will be talking about that too. Okay, so percentage error due to neglecting the kinetic energy terms. So you are going to cancelling out that C2 square by 2 minus C1 square by 2, and what will be remain as W is equal to change in enthalpy plus change in potential energy. So the work done will be 887.05 kilowatt, and if you consider it as a percentage error, the percentage error will be like 0.057 percentage. It's not 57 percentage, it is 0.057 percentage. Okay, and if you consider that percentage error due to neglecting the potential energy term, and if you cancelling out that Z into Z1 minus Z2, what will happen? The work done as 886.6 kilowatt, and the percentage error will be around 0.0067 percentage. It's not 67 percentage, it's 0.0067 percentage. It is very, very minimum. That's why we are neglecting those terms as that is potential and kinetic energy terms, even though here potential energy has been given. If you neglecting out, there is not much of change in the power calculation. Okay, so this is one important thing you need to look out, and write down the next question. Okay, problem number 15, that is the electronic components of a computer are cooled by air flowing through a fan mounted at the inlet of a electronic enclosure. A steady state air enters at 20 degrees centigrade, 1 atmosphere for noise control. Okay, the temperature the velocity of entering air cannot be exceed as 1.3 meter per second. For temperature control, the temperature of air at exit cannot exceed 32 degrees centigrade. The electronic components receive respectively 80 watt and 18 watt of electric power. Determine the smallest fan inlet diameter in meter for which limits on the entering air velocity and exit air temperature are met. So this is simple, air cooler. Okay, simple air cooler. If you are using a laptop, there is a cooler will be mounted at the bottom of the computer, right? So a fan is mounted at the bottom of a computer to reduce a temperature of a laptop. Okay, so write down all these given data has been given. So this is a motor. Okay, so you need to find out that fan diameter of a fan which met the conditions, like it should control the temperature as well as it should control the noise as well. Okay, so write down that temperature, pressure, velocity cannot be exceed as 1.3 meter per second, and temperature cannot be exceed as 32 degrees centigrade, and work done will be like 80 and 18 watt of work should be given to that electronic computer. So minus 80 minus 18, that 98 of work done, sorry, 98 of watt the power we need to give in order to cool the laptop. Okay, here the work done is negative because we are going to supply the work done to that system. It is not we are getting the work done by the from the system, we are giving the work done to the system, so it will be considered as a negative. Okay, so we need to find the smallest inlet diameter. Okay, so write down that energy equation. So system is said to be control volume, so kinetic energy and potential energy is neglected here, and the heat transfer from the outer surface of the electronic enclosure to the surrounding is negligible because we are pulling the heat from a computer and sending to the environment, so there is no heat transfer from the surroundings to the system. Okay, so the heat transfer is taking place from the system to the surrounding, not the surroundings to the system. So here the heat transfer from the outer surface to the electronic enclosure should be neglected, and so this is the steady flow energy equation. If you cancelling out that heat transfer and potential and kinetic energy terms, remaining terms as the W will be W is equal to M into H2 minus H1, where mass flow rate, that is M is equal to volumetric flow rate divided by specific volume. We have seen it in the previous videos. So volumetric flow rate will be calculated as area into velocity and divided by specific volume. So here M is equal to, area 1 is equal to M into V1 divided by C1. Substitute all the terms, you will get mass flow rate, area. Okay, so here W is equal to M into Cp into T2 minus T1, and M is equal to minus W divided by Cp into T2 minus T1, and substitute that M value. Okay, so M is equal to A1 C1 divided by V1, right? Substitute that term here. So what you will get as A1 is equal to 1 by C1 into minus W divided by Cp into T2 minus T1 whole into RT1 divided by P1. Okay, so substitute all the terms in that equation, you will get area of that fan, that is 0.00518 meter square. Okay, so we know that the fan is a circular diameter, so area of a circle is equal to, that is pi d square divided by 4, and d square as rearrange those terms, and you will get diameter as 0.0812 meter. Okay, so this is the smallest fan diameter which we need to design. Okay, so that's it from this. Thank you for watching.